Good day, everyone. Today we're going to discuss all about Atterberg limits. Atterberg limits are various moisture contents that are very useful in foundation designs. Atterberg limits were introduced by Albert Atterberg in the early 1900s, a Swedish scientist that developed a method describing the consistency of fine-grained soils with varying moisture content. So he described the behavior of soils at various moisture content. So if we look at this one, at this picture, this soil has no moisture content and behaves like solid. In this case, this is a moist soil. And in this case, it is already submerged in water and behaves like liquid. So, Albert Atterberg described the states of soil at various moisture contents. So, ang sabi niya, there are four states of soil, what we call the solid, semi-solid, plastic, and liquid state. So, pag ang lupa, walang tubig, it behaves like solid. And pag dinagdagan na natin ng tubig yan, it will behave like semi-solid na. Yung moisture content na nagpabago or nag-start, kung saan nag-start yung ating lupang mag-behave as semi-solid state, from solid to semi-solid state is what we call the shrinkage limit. And then, pag nasa semi-solid state na siya, dagdagan ulit natin siya ng tubig. Pag dinagdagan natin siya ng tubig, it will reach its plastic state. And yung moisture content, kung saan nagsimula yung pagbabago ng behavior ng ating lupa from semi-solid state to plastic state is what we call the plastic limit. So it is the boundary between the semi-solid state and the plastic state. And then, at its plastic state, dagdagan ulit natin ng tubig. So, pag dinagdagan ng tubig, yung lupa, it will behave like liquid. So, yung moisture content, again, that started to the soil to behave like a liquid is what we call the liquid limit. So, it is the boundary between the plastic state and the liquid state. So, at moisture content at increasing, magbabago ang ating state ng lupa. From solid state to semi-solid to plastic state and therefore to liquid state. The first moisture content that we're going to discuss is what we call the liquid limit. So liquid limit is the moisture content in percent required to close a distance of 12.5 or 0.5 inches along the bottom of the groove after 25 blows. And the first person who studied the liquid limit is Arthur Casagrande. Arthur Casagrande is an Austrian-born American civil engineer who made important contributions to the fields of engineering, geology, and geotechnical engineering during its infancy. He introduced the device called CASAGRANDE cup device in order to determine the liquid limit. So this is a picture of a liquid limit device or a CASAGRANDE cup device. So this device consists of a brass cup and a hard rubber base. And the brass cup can be dropped onto the base by a cam operated by a crank. So this is a crank and this is rotated. And to perform the liquid limit test, one must place a soil paste in the cup. A groove is then cut at the center of a soil pot with a standard grooving tool. And there are two types of grooving tools. Those are flat grooving tools and the wedge grooving tool. So, ang definition ng liquid limit is the moisture content at 25 blows that closes at 12.5 mm or 0.5 inches. So, ang isang rotation nito is 1 blow. Pero, pag nilagyan natin to ng lupa, at may tubig yung lupa, tapos i-cut natin using the grooving tool, hatiin natin, at i-rotate natin, hindi natin ma-assure na mag-close yung ating lupa at 25 blows agad-agad. Kaya meron tayong 4 trials. So, yung 4 trials na yun yung ating ginagawa sa testing ng ating liquid limit. So, una, kukuha tayo ng lupa. Ilalagay natin dito sa cup na ito. Tapos, yun dapat ay medyo moist lang. Tapos, hatiin natin yung ating lupa. Pag hinati natin siya. And then, para siya mag-close at 12.5 mm, i-rotate natin itong crank na ito. Bibilangin natin kung ilang blows. Pag nag-close na siya at 12.5 mm, kukunin na natin yung lupa. Para makuha natin yung moisture content ng lupa, ilalagay natin siya sa oven. So, i-weigh natin yung sample natin bago siya ilagay sa oven. So, yun yung wet weight. And then, after natin i-oven for 24 hours, at mag-constant na yung weight niya, i-weigh ulit natin and then it will be the oven dried weight. Kapag sinubtract ninyo yung wet weight the dry weight from the wet weight, all over the dry weight, it will be the moisture content at corresponding blows. Tapos, syempre nga, hindi natin siya basta-basta makukuha yung moisture content natin at 25 blows. Kasi diba, ang definition ng ating liquid limit is the moisture content at 25 blows. So, yung lupa natin na yun, konti-konti munang moisture content yung ilalagay natin. Tapos, dadagdagan ulit natin siya ng tubig. Tapos, pag nilagyan na natin siya ulit ng tubig, ilalagay na natin dito yung sample. So, i-flatten, hatiin ng groove, tapos, para ulit mag-close at 12.5, i-rotate natin at bibilangin natin kung gaano kadaming rotation bago siya nag-close ng 12.5 mm. So, yung blows na yun, ay bibilangin natin and then kukuha ulit tayo ng sample dito, i-weigh natin bago siya i-oven and then i-weigh after oven drying and then pag constant na yung weight, saka natin kukunin yung moisture content. So, magkakaroon tayo ng 4 to 5 trials. So, dadagdagan natin siya ng dadagdagan ng tubig para makakuha tayo ng 4 or 5 partners, so or pairs ng moisture content versus the blows. So, yung CASAGRANDE cup device natin, ganito. And then, ito yung grooving tool, ito yung sizes and yung kanyang measurements. So, in the laboratory, ganito siya ang itsura. Ito yung ating lupa na nilagay. If you will imagine, siya ay medyo moist and then flat pa siya. Tapos hinati siya ng grooving tool dito. Tapos kapag ni-rotate na natin itong crank, magko-close siya at 12.5 mm. So pag nag-close na siya, that's that time na mag-stop na tayo and kuha tayo ng sample dito. Kukuha tayo ng sample at kukunin natin yung moisture content nito. Again, 4 na trials or 5 trials ang gagawin natin kasi nga, hindi siya agad-agad mag-close yung lupa at 25 blows Saktong pag ni-rotate natin ito, hindi siya mag-close agad-agad at 25 blows. So, pwedeng lumagpas or pwedeng mag-close agad-agad siya kahit hindi pa niya na-reach yung 25 blows. Kaya meron tayong semi-logarithmic table na pinaplat natin yung moisture content versus the number of blows. And then, saka pa lamang natin makukuha yung number of blows at yung moisture content at 25 blows kapag plinat na natin, and that will be the liquid limit. So, ganyan siya. Mag-close siya dito at 12.5 mm. Ito. Dapat. So, ganito yung magiging flow curve natin. So, if you can see, at corresponding moisture content, ay may corresponding number of blows din. Ito. Ito yung mga test results. Itong plinat natin. Naka-plot siya. Yan. Ito yung moisture content. At yung moisture content at 25 blows, that will be the liquid limit. Ang tawag dito is flow curve. There is another method in determining the liquid limit, and that is what we call the fall cone method. In this test, the liquid limit is defined as the moisture content at which a standard cone of apex angle 30 degrees and weight of 0.78 Newton or 80 gram force will penetrate a distance d equals 20 mm in 5 seconds when allowed to drop from a position of point contact with the soil surface. So, ang pagkakaiba ng CASAGRANDE cup device, it's the moisture content at 25 blows. Ito namang fall cone method, it's the moisture content at 20 mm penetration. So this is an example of a fall cone apparatus. So, para makuha natin yung liquid limit, lalagyan natin to ng lupa with corresponding moisture content. So, ang lupa, kapag siya ay medyo tuyo, hindi agad magpe-penetrate itong ating cone. Kaya hindi siya agad malubog. So, magkakaroon din siya ng 4 or hanggang 5 na trials para makuha yung moisture content natin. Dahil, again, hindi natin basta-basta masisigurado na kapag nilubog natin itong cone na ito dun sa lupa, ay 20 mm yung penetration niya agad-agad. So, magkakaroon ulit tayo ng trials. So, first trial, lalagyan natin ng lupa yung itong cylinder na ito. Tapos, ipipenetrate natin itong cone. And then, pag lumubog na siya, within 5 seconds, kukunin natin yung penetration, susukatin yung penetration. And then, dadagdagan ulit natin ng moisture content para mag-penetrate ulit yung cone. Tapos kapag medyo mas moist na yung lupa natin, mas malubog siya. Kaya habang na dami yung moisture content, mas malalim yung penetration ng ating cone. So, there will be 4 to 5 trials. So, yung flow curve by fall cone method ay ganito. So, we also plot the moisture content versus the penetration. So, at corresponding moisture content, may penetration ng cone. So, there are 4 trials here. At yung liquid limit or yung moisture content na nakatapat sa 20 mm penetration, that would be the liquid limit of the soil. And that is how you measure the liquid limit using fall cone method. Another moisture content that we're going to discuss is what we call the plastic limit. Plastic limit, again, is the boundary between the semi-solid state and the plastic state of the soil. So the plastic limit is defined in as the moisture content in percent at which the soil crumbles when rolled into threads of 3.2 mm in diameter. So the plastic limit is the lower limit of the plastic stage of the soil and is performed by repeated rollings of an ellipsoidal soil mass by hand on a ground glass plate. The procedure for the plastic limit test is given by ASTM in test designation D-4318. So, yung ating lupa, ito yung lupa, yan ay mas malaki pa dati yung diameter. Tapos, i-roll natin siya ng i-roll hanggang ma-reach na yung 3.2 millimeter diameter hanggang lumiit yung ating diameter ng lupa. So, magiging ganito na siya. So, para kayong nagamasa ng tinapay, muna yung ganun kalaki, tapos naliit siya ng naliit, hanggang mag-crumble. So, yung pag nag-break na yun dun sa gitna, nag-start na siyang mag-crumble. That's when you will know that you have reached the plastic limit of the soil. So, pwede din nating makuha yung plastic limit using the fault cone method. So, this can be achieved by using a cone of similar geometry but with a mass of 2.35 Newton or 240 gram force. So, ilang gram force yung nauna natin? Balikan natin yung sa ating fault cone method. Ang ginamit natin kanina ay 80 gram force or 0.78 Newton para makuha yung liquid limit at 20 mm penetration. But in plastic limit, in the case of plastic limit, para makuha naman yung plastic limit, kailangan ay ang mass ng cone natin is 2.35 Newton or 240 gram force. So, meron ding 3 to 4 tests at varying moisture contents. Ganun din ang procedure sa pagkuha ng liquid limit. And then, ipa-plot ulit natin siya at kung ano yung moisture content na nasa tapat ng 20 mm penetration, that would be the plastic limit. So, papaano? Ganyan. So, this will be the difference. Ito yung 0.78 Newton na ginamit natin. Ito naman yung sa plastic limit. 4 na trial din siya at yung nakatapat na moisture content dun sa 20 mm penetration, that would be the plastic limit of the soil. And then, we tackle about the plasticity index. So, plasticity index is just the difference from the liquid of the liquid limit and the plastic limit. So, pag daw ang plasticity index natin is 0, it is described as non-plastic soil. If it's 1 to 5, it's likely plastic. If it's 5 to 10, its description is low plasticity. And 10 to 20, the soil has medium plasticity. 20 to 40, the soil has high plasticity. And if it's more than 40, the soil has very high plasticity. So, in this table, you will see the typical values of liquid limit, plastic limit, and activity of some clay materials. So, we have kaolinite, aylite, morillonite, halloysite, dehydrated and dehydrated, attapulgite, and alupane. So, these are types of clays, and these are the possible ranges of their plastic limit, liquid limit, and activity. And last moisture content that we are going to tackle is what we call the shrinkage limit. So again, the shrinkage limit is the boundary between the solid state and the semi-solid state of the soil. So it is the moisture content in percent at which the volume of the soil mass ceases to change. And shrinkage limit tests or ASTM 2007 test designation D-427 are performed in the laboratory with a porcelain dish about 44 mm or 1.75 inches in diameter and about 12.7 mm high. The inside of the dish is coated with petroleum jelly and is then filled completely with wet soil. Excess soil standing above the edge of the dish is struck off with a straight edge. The mass of the wet soil inside the dish is recorded, and the soil pat in the dish is then oven-dried. The volume of the oven-dried soil pat is determined by the displacement of mercury. So, in the field, in the laboratory, para makuha natin yung shrinkage limit, meron tayong porcelain dish. So, this is an example of porcelain dish. So, yung porcelain dish daw natin, i-coat natin siya ng petroleum jelly. Tapos, yung ating lupa, lalagyan natin siya ng tubig. And then, kapag siya ay moist na, pupunuin natin yung ating porcelain dish ng lupa at i-weigh natin yung kanyang weight bago natin siya i-oven dry. Kapag ang lupa ay natutuyo, nag-shrink siya. So, Pag pinalaki, ay ganito ang magiging image niya. Maliit yung ating lupa. Mag-shrink siya dahil tumuyo na. So, yung para malaman yung weight nung pagbabago nung lupa natin, kailangan natin gumamit ng mercury. Itong porcelain dish na to, nalagyan natin ng mercury. So, syempre, yung mercury, ang ma-occupy lamang niya na space ay yung space lamang yung space lamang nung nag-shrink. So, para makuha natin yung weight, 'di ba, may specific gravity tayo ng mercury na 13.6. And then, i-weigh natin siya. So, para makuha yun, makukuha natin yung weight gamit yung specific gravity ng ating mercury. And you will get the difference between this soil mass and this soil mass. And then, this is the actual picture in the laboratory. So ito, bago siya i-oven dry, if you recognize, if you'll see it, walang space. And then nung tumuyo na siya, may space siya. At ito yung ina-occupy nung mercury pagkatapos ng testing. Ito ay oven dried na. And para makuha natin yung shrinkage limit, it's equal to the mass before oven drying minus the mass after oven drying all over the mass after oven drying multiplied by 100 minus its initial volume minus the final volume after over drying all over the mass after oven drying multiplied by the density of water multiplied by 100. So, ang sagot dito is in percent kasi pareho na natin siyang minultiply sa 100. And then, we also have shrinkage ratio. So, shrinkage ratio and specific gravity can be solved with this formula. SR is equal to M2 over V2, density of water, and specific gravity is equal to 1 over SR minus SL over 100. So, this is in percent. Kaya siya may 100 dito sa baba. And we also have the liquidity index. So, the liquidity index is the relative consistency of a cohesive soil in the natural state. And it is equal to the moisture content minus the plastic limit over liquid limit minus the plastic limit. Or, because LL minus VL is equal to the plasticity index, it can also be written as the moisture content minus the plastic limit all over the plasticity index of the soil. And we could define the behavior of soil with the liquidity index. Ang sabi, the moisture content for a sensitive clay may be greater than the liquid limit. In this case, Li is greater than 1. These soils, when remolded, can be transformed into a viscous form to flow like a fluid. So, if Li is greater than 1, it flows like a liquid. Soil deposits that are heavily over-consolidated may have a natural moisture content less than the plastic limit, and in this case, Li is less than 0. And when Li is less than 0, characteristic of soil is brittle solid. If Li is less than 1, it is plastic, and when Li is greater than 1, it is in its liquid state. When liquidity index is also 0, it means the soil is at its plastic limit. And when Li is greater than 1, it means that the soil is at its liquid limit. So this is the illustration. So when Li is equal to 0, it is at its plastic limit. And when Li is equal to 1, it is at its liquid limit. So at greater than 1, the soil behaves like a liquid. Also, we have what we call the consistency index in order to define the behavior of the soil. CI is equal to the liquid limit minus the moisture content all over the liquid limit minus the plasticity index. If moisture content is equal to the liquid limit, the consistency index is 0. Dahil magiging 0 ito. LL is equal to moisture content, the consistency index will be equal to 0. If moisture content is equal to Pi, then Ci is equal to 1. If this will be equal to Pi, Ci will be equal to 1 kasi pareho lang yung value. Pareho yung value. Then Ci will be equal to 1. Okay, let's move on to sample problem in order for us to understand more about the liquid limit, the plastic limit, and the shrinkage limit. So, sample problem number 1. A liquid limit test conducted on a soil sample in the CAF device gave the following results. So, meron daw number of flows and water content. So, 19, 14, 45.2, 23, 39.8, 27 blows, 36.5, and 40, 25.2. So, two determinations for the plastic limit in the laboratory gave water contents of 20.3 and 20.8%. So, we have to determine the liquid limit and the plastic limit, the plasticity index, the liquidity index if the water content is 27.4%, and the void ratio at the liquid limit if GS equals 2.7. And if the soil were to be loaded to failure, what would you expect? Would you expect a brittle failure? So, let us first solve for the liquid limit. So, we have the results of the liquid limit here. And this is a logarithmic scale. If you will notice, hindi siya yung typical scale natin na pare-pareho yung spaces. If you will look at the table, habang nalaki yung number of blows, naliit yung spaces. Kasi this is a logarithmic scale. Ito lang yung pare-pareho, pataas. Pero ito, sa baba, sa number of blows, magkakaiba ng spaces yan. Because hindi siya yung typical natin na pag-graph. This is a semi-logarithmic scale. So, paano natin siya computing yung liquid limit? Again, ang given ay number of blows and water content. So, this is a result of CASAGRANDE cup device test or using the CASAGRANDE cup device. So, para makuha natin yung liquid limit, we have to know the value of the moisture content at 25 blows. If you will look at the results, wala namang 25 dyan. So, hindi natin basta-basta makukuha yung liquid limit. Kailangan natin siyang i-plot. So, if we are going to plot it, so isang point ito, isang point, isang point, isang point. So, we have 4 points. At para makuha natin yung moisture content at 25 blows, kailangan natin itong malaman kung saan matapat. Okay, so let's first plot the first point. So, magsimula tayo dito sa dulo. 40 and 25.2. So, if we're going to plot 40, so dito siya, and 25.2 lies somewhere here. So, this is the first point. And then, the second point, 27 and 36.5. So, number of blows is 27. So, it lies somewhere here. And the water content is 36.5. So, here. So, this is the second point. And then, 23 versus 39.8. 23 is here. And 39.8 is somewhere here. So, that's the third point. And last point, 19 versus 45.2. 19 is where? 19 lies somewhere here, the number of blows, and 45.2 is there. So let's graph the last point. And then, we draw a straight line. Again, the straight line is the flow curve. And para makuha natin yung liquid limit, it is the moisture content at 25 blows. So, ito, ang moisture content ng ating lupa ay about 38%. So, the liquid limit of the soil will be equal to 38%. Okay? And then, after that, we get the plastic limit. So, ang sabi dun sa problem, there are two determinations for the plastic limit in the laboratory. So, meron daw 20.3% and 20.8%. Para makuha natin yung plastic limit, we just get the average of these two moisture contents. So, PL, therefore, is equal to 20.3 plus 20.8 all over 2. Plastic limit is equal to 20.55%. And then for letter B, we have to know the plasticity index. So in order for us to get the plasticity index, it is just equal to the liquid limit minus the plastic limit. So we all know that the liquid limit is equal to 38 minus the plastic limit, which is 20.55. And that would give us the answer, which is 17.45%. And that is the value of the plasticity index of the soil. And then, we already solved for the liquid limit, the plastic limit, and the plasticity index. We now solve for the liquidity index if the water content is 27.4%. And the void ratio at the liquid limit if the specific gravity is 2.7. Also, if the soil were to be loaded to failure, would you expect a brittle failure? So let's solve for the liquidity index first. So ang sabi, the moisture content is 27.4 minus 20.55, that is the plastic limit, all over the plasticity index, which is 17.45. And that would give us the answer 0.393 or 39.3%. That will be the liquidity index. Also, we have to know the void ratio at liquid limit. So we have to assume that the soil is saturated at liquid limit. And for a saturated soil, we know that E is equal to WGS. But we have the relationship between the moisture content, the specific gravity, and the degree of saturation, and the void ratio, that is equal to SE equals MCGS, or equal to SE equal to WGS, or that's why if it's saturated, S will be equal to 1, and it will just be equal to E equals the moisture content multiplied by the specific gravity. Thus, the void ratio at liquid limit is equal to the liquid limit multiplied by the specific gravity. That will be equal to 0.38 multiplied by 2.7, which will give us the value of the void ratio at liquid limit, which is equal to 1.03. And lastly, will the soil experience a brittle failure? The answer is no. Brittle failure is not expected as the soil is in plastic state because the liquidity index lies from 0 to 1. And therefore, that would be the answer for problem number 1. Next problem is for shrinkage limit test. So these are the results of the shrinkage limit test. So initial volume of soil in a saturated state is equal to 24.6 cubic centimeter. Final volume of soil in a dry state is equal to 15.9 cubic centimeter. Initial mass in a saturated state is equal to 44.0 grams. And final mass in a dry state is equal to 30.1 grams. So we have to determine the shrinkage limit of the soil, the shrinkage ratio, and the specific gravity of the soil solids. So in order for us to get it, we have to solve first for the shrinkage limit. And we know that SL is equal to quantity M1 minus M2 all over M2 multiplied by 100 minus quantity V1 minus V2 all over M2 multiplied by the density of water multiplied by 100. Just by substituting the values, we get 44 minus 30.1 all over 30.1 multiplied by 100 minus quantity of 24.6 minus 15.9 all over 30.1 times the density of water in gram per cubic centimeter is 1. And then multiply it by 100, we get the value of the shrinkage limit, which is equal to 17.275%. And if we get the shrinkage ratio, it's just equal to M2 over V2, density of water. We just substitute the values in the formula, and we get 30.1 all over 15.9 multiplied by 1. Therefore, the shrinkage ratio is equal to 1.893. And lastly, we get the specific gravity. We know that the specific gravity of the soil is equal to 1 over SR minus shrinkage limit all over 100. If we substitute the value, it will be equal to 1 over the shrinkage ratio is equal to 1.893 minus the shrinkage limit is equal to 17.275 all over 100, and that will give us the specific gravity of the soil solids, which is equal to 2.813. And that would be the solution for problem number 2. And then that would be all. And if you have any questions, you can always contact me and message me. Thank you.